This is section 7.4, and what I want you guys to do is I want you guys to copy down the notes that I'm going to write down here and follow along as I go through in your note packet. I'm going to write these through, and then that way you can have an idea of what's going on when it comes to your homework today. Okay? So, again, continue to follow along as we go through on this and write down the things that I write down. Okay? Our objective for this section, section 7.4, is to find and use relationships in similar right triangles. Okay, so we're going to take similar right triangles and find relationships about them that are going to make them similar. Okay, our essential understanding here, when you draw the altitude, we're going to talk about what this word means here in just a second, the altitude, to the hypotenuse of a right triangle, you form three pairs of similar right triangles. Now, let's talk about that word. Let's talk about the word altitude. What is it? The altitude of a triangle, okay, is the perpendicular segment from a vertex to the line containing the side opposite of that vertex. Okay, there's two possible ways here that you can make altitudes. One inside a triangle, okay, it goes from one vertex to another side opposite of that, and it forms a 90-degree angle every time. Or you can draw an altitude on the outside of a triangle where you draw it down, again, comes down from a vertex to a line of the triangle opposite of that if we were to continue this through, and it forms a right angle. Okay, so that's what an altitude is. Now, if you draw an altitude in similar right triangles, what it will do is it will create three right triangles that are similar. So theorem 7.3 says the altitude to the hypotenuse of a right triangle divides the triangle into two triangles that are similar to the original triangle and to each other. So, as you are looking at this picture here, when you draw this altitude from the right angle to the hypotenuse, it's going to create three triangles that are similar. Okay? And what they've done here for you is they've split this up. So they've taken triangle ADC and they've drawn it separately. They've taken triangle CDB and drawn it separately. And then we also have the big triangle. Now, if you look, if the triangles are similar, remember all the sides are proportional and the angles are congruent. So as I look at this here now and I show this, I could say angle B in this case is congruent to the big angle B of the big triangle, and it's also congruent to this triangle. Okay, so all those angles, angle B, angle C, and angle B are all the same. Going to be congruent to each other. Same as angle A and angle A in that picture, along with angle C in this picture. Okay, and again, obviously, we have the fact that we also have the right angles of the triangles are also congruent to each other. Okay, so we can also say, as you look at these, okay, we can also say that the sides are proportional. Now, again, if I drew this out, it would be side AB over side AC equals side BC over side CD, and that's going to equal side AC over side AD. Okay, that would be the simplified version of it. All right. So, what theorem 7.3 says now is if we draw an altitude, we can create three similar right triangles. Okay, so let's go to the example now below, and let's take a look here at the identifying similar right triangles. What similarity statement can you write relating the three triangles in the diagram? So you'll notice you've got the big triangle here. This is the altitude. Okay, so we're going to start with the very big triangle. Let's name the big triangle. And we're going to name the big triangle XYZ. And it's going to be similar to triangle. Now, we named it XYZ. So we went short leg to right angle to the second shortest leg. We did not include the hypotenuse segment. Okay, so we're going to name this similar. Let's name the second biggest one. When we name the second biggest one, again, we're going to start with a short leg, go to the right, start with a short leg, go to the right angle, and across. So it's going to be triangle YWZ. And that's going to be similar to the smallest one, which in this case is going to be x, w, v. Okay, again, we go shortest leg to right angle to the next leg. Okay? Those are the three triangles that are going to be similar. We can do the same thing over here on this set. What similarity statement can you write relating the three triangles in the diagram? Okay? So as you look at this, let's start out with the big triangle. Okay? So I'm going to redraw these three triangles down here. Okay? And I'm going to label this, the very first one I'm going to label is going to be the big one. Okay? So the big one, in this case, this is Q, this is P, and this is R. Okay? Let's take the second largest one. Okay? This is going to be, if I match them up, this is going to be P, the right angle is S, and this is R. And then the smallest one, this is Q, this is S, and this is P. Okay, so now as you look at these, I've separated these triangles out for you to give you kind of a better idea how to write these as a similarity statement. So I'm going to write this as triangle QRP is similar. I went here again, I went Q to R to P. So over here, I'm going to go P to R to S. Triangle PRS. And that's similar to triangle QPS. Okay, so they're going to have you identify the three triangles that are similar in your pictures. So on the separate sheet of paper, what I want you to write down is I want you to draw down a right triangle. Like so. Okay? And then we're going to create an altitude. From this vertex to the hypotenuse, we're going to say this guy is 90 degrees. That guy's 90 degrees. And what I'm going to do is I'm going to put letters in for sides. So it's easier for you to match up and figure out what sides you're going to have to be able to calculate. Okay? Because you can't calculate this the good old-fashioned way. And it's much easier to do it with this shortcut way than it is to try and write proportions all the time. Okay? So I'm going to name this side A. This is going to be side B. This is side D, this is side E, side F, and the whole side is C. Okay? And again, this is using the geometric mean. Okay? What the geometric mean says is I can find any one of these sides as long as I have two of the sides. So here's how we're going to calculate this. To find side F, it's going to equal the square root of D times E. To find side A, it's going to equal the square root of side C times side D. And if I take side B, this is going to equal the square root of side C times side E. Now, again, how do I come up with that? That goes all back to the proportions, okay? And I don't have a ton of time here to discuss this. So I'm going to kind of give you the shortcut and let you work with it. All right? So, again, I can give you any one of these sides, give you a couple different sides, and you can calculate the value of each one of these. And that's essentially what you're going to do at the end of this section, okay? So, go ahead and turn back to the second page of your notes, and I'm going to go through some of these examples. Okay, the next part we're going to do a combination. I want you to put this on your back page if you have some open space, or you may have to put some of this on a separate sheet of paper. But this is where we talked about yesterday, we talked about the geometric mean and how to actually calculate it. This is where the geometric mean is going to come into play. Okay? So when we first start, we've got the corollary to Theorem 7.3. They've got two different things with the corollary. Okay? And you'll notice how they set up proportions accordingly in this case. And I'm going to completely skip over all of this stuff, okay? Because when we're trying to find different sides of these right triangles, remember there's three of them here, there's one simple way to do this, okay? Okay, so let's take a look here at some of these examples down here. Okay, and again, if you have that paper with you again, okay, where I just drew that triangle, it's going to help you out quite a bit. And what I'm going to do is I'm going to draw this triangle over here. To your left, so that you can see this, and you have it here to look at. Again, you have an A, you have a B, an F, a D, an E, and a C. Okay. So now what you're going to have to do is you're going to have to try and match up the triangle to this triangle right here. Okay. So essentially, you're going to take this triangle, you're going to flip it over to match it up. Okay. Now, as you look, what two sides, letter-wise, from this triangle do you need in this one? And if you see, this is Y, that's in the place of F. So we're going to try and find F. This right here is X, that's in the place of B. Okay? So again, I'm going to use those concepts here to find my values. So, as you look, you notice that you have actually side F over here is side Y. So when I go to calculate this, side Y, which is F, is going to equal to the square root of D times E. And again, this right here is D. This right here is E. So it's going to be the square root of 12 times 4. Okay? So now, Y equals the square root of 12 times 4. If I calculate 12 times 4, this goes back to square root stuff. This is the square root of 48. And the largest perfect square that goes into 48 is 16. Which, if I simplify this, Y is going to be 4 times the square root of 3. Okay? Now, I still got to find X yet. Now, X is the same as side B. So in this case, X is going to equal the square root, and if you remember, B is C times E, and C was the whole segment. Okay? So the whole segment is 16 times E, which is 4. Now, again, this is going to be the square root of 16 times the square root of 4. What's the square root of 16? That's 4 times the square root of 4, which is 2. So in this case, X is going to be 8. Okay? All right, now, let's take a look down here at the bottom of these three examples at the bottom. I'm going to skip over the example there to the right just for the sake of time here. Okay? All right, now, this time they give you something a little bit different. They give you a whole segment so that you have C, you're looking for E, and you have side B. Okay? So again, I'm going to look at this B, as we look at this here, again, F equals the square root of D times E, and A equals the square root of C times D, and B equals the square root of C times E. Okay, well 6 in this case is side B. Okay, so I know I'm going to have B equals the square root of C times E. And B is in the number 6. Side C is 12 times E, which is the letter A. Okay, now how do I solve this? Got a square root. I'm going to take and square both sides. So this now becomes 36 equals, the square and the square root will cancel, and I get 12A. And if I divide by 12 on each side, I get A to equal 3. Okay? Let's take a look at number 5. As you can see on number 5, I've got, this is F. This right here is E. And this right here is D. So I need to find F. F equals the square root of D times E. F is X. Square root D is 8 times E is 6. So now this is going to be the square root of 48, which is going to be the square root of 16 times 3, which is going to be 4 times the square root of 3. So X is going to be times the square root of 3. Okay? All right, now let's take a look at number 6 quickly here. Again, number 6, we're looking at, in this case on number 6, we are looking at, we've got, in this case, this is side B, this is C, and this is E. Okay, so again, B equals the square root of C times E. B is 10. The square root of C, which is 24, times B is E. I'm going to square both sides to get rid of the square root. So 100 equals 24B, because the square root and the square cancel. Divide by 24, and B in this case is going to be a decimal of 4.2. Or, if you left it as a fraction and reduced it, you get 25/6. Okay, now, this is section 7.4, and I want you to use these examples to try and help you work through some of this homework stuff, okay? You've got the rest of the class period now to use your time here to work on the worksheet and complete the worksheet.